Hello everyone, my name is Micah Villmow and I'm an employee at AMD, and today I'm going to talk to you about the AMD OpenCL Compiler. We talked to you today about how AMD utilizes the LLVM toolchain to create a cross-platform heterogeneous compiler. So I'm going to talk about today, I'm going to start off with a high-level overview of our compiler toolchain. Then I'm going to talk about our target backends. I'm going to talk about the CPU compiler path versus the GPU compiler path. And I'm going to have some ideas that would simplify some of the things that I've had to do. And mainly because I'm a GPU backend engineer, most of this talk will be GPU focused. But I will touch on the CPU side a little bit. So looking at our compiler toolchain, we start off with the front end, which is an EDG-based front end that is extended to accept OpenCL, and it produces LLVM IR. There will be a talk on BOF on OpenCL a little bit later, also with a talk on EDG to LLVM. So if you want more information on that, you can go to those talks, and I'm not going to go into too much detail about that. Our linker is modified based on the efficient JIT presentation from LLVM 08. And we use this to link in OpenCL libraries, which are bitcode files, and also some device-independent algorithms and functions. After the linker, we split off into the optimizations. The GPU optimizations and the CPU optimizations are two separate paths in our compiler. And so I'll go into a little bit about how they are different and what we do there. And then I'll go into the backend. So our two code gens, we have the AMD IL Backend, which is an in-house product that we've been working on for a little over 2 years. And then we have the x86 backend, which is from LLVM core. And then we have the binary generation. So for the target binary generation, we have the CAL compiler, which is from the OpenCL Stream SDK. And then we also, for the x86 side, we have AS and LD. So going on to the target backends. The CPU backend targets SSE2 plus devices. So anything that supports SSE2 or later, we target it. It is the LLVM core x86 backend, but we do have some minor bug fixes and changes to work with OpenCL. There's more information on this in the Twin Peaks paper that AMD had presented at PAC 2010. The GPU backend is a custom backend that we use that targets AMD IL. It is AMD IL, I'll go into a little bit later, but the spec is in the Stream SDK, and it's a language that we use that compile down to the ISA for our GPU. There are a lot of constraints in this language that are very unique, and they don't exist in most other languages, and that causes some issues for CodeGen. So let's start off with the CPU compiler path. The CPU compiler path mainly has the standard optimization passes. However, we do have to make some changes to the backend to deal with just quirks of OpenCL or just conformance issues. So one of them is we expand all the memops. So I don't know all the exact details, but we do expand these into a sequence of loads and stores. It might be because of OpenCL's requirements of large vector types and alignments. Another thing is we have custom ulong to float conversions on Win32. This has to deal with the fact that Win32 sets different rounding mode registers than on Linux. And so we have to do a different float conversions in the backend since the one that's already there doesn't work correctly. We have custom data alignments. So one of the constraints about OpenCL is that we have stuff up to a double 16 vector type that we have to support. And this is a 1 kilobyte or kilobit data type with a 1 kilobit alignment constraint. So we have everything from an 8-bit all the way up to 1 kilobit on all the powers of 2s. We disable MMX generation because we only support SSE2 or later CPU devices. And also, we have Jan Sojin has been working with a couple other people to implement the MC binary emitter for the x86 backend. And so once we do that, we can get rid of the AS and LD, and we have just the x86 backend emitting binary. So that'll simplify our compiler path, and that's something that he's been working on and getting into LLVM core. So now I'm going into more of my specialty, which is the GPU compiler toolchain and the compiler path. So for the GPU optimizations, we had to modify quite a lot of flow control optimizations. One of the problems with the GPU is that flow control is very expensive. It can be up to 40 cycles for a single flow control instruction, whereas a math instruction like sine or cosine is amortized to a single cycle. So what we've seen is an optimization like loop unswitch. It would take a loop with some control flow and then generate even more control flow than was in the original source program, and this was having a very detrimental performance issue. So we disabled that, and then we moved on to simplify CFG. There is a special instruction in OpenCL called barrier, or a special function called barrier, which is an execution barrier, not just a memory barrier. So this function, if it gets duplicated, causes undefined behavior on a GPU. So we had to modify simplify CFG to disable duplication of this function in certain situations. Another optimization pass is jump threading. Again, there were certain situations where the barrier function call would get duplicated and cause undefined behavior. Now, there are some situations where barrier can get duplicated legally, like loop unrolling. But if you do inlining and the caller is being called from in the if and the else of a flow control, but the callee has a barrier, you then duplicate it on inlining. So we had to do a couple optimization modifications to the optimizations pass so that barrier was no longer duplicated. Loop simplify. There are some situations where loop simplify does really good work, but there are some situations which causes performance degradation based on register pressure and other issues. So we disable loop simplify so that the CAL compiler will do that optimization since they have more register pressure information during this time. We're also adding a loop unrolling pragma. So loop unrolling by default uses I believe it's a weighted calculation on how far it should unroll. But there are function calls, depending on the architecture, they could take 1 cycle or they could take 1,000 cycles. So we had to disable loop unrolling because it was conflicting with loop unrolling that's done in the CAL compiler, which is the IL to ISA generation. But we did also create a pragma so you can specify, okay, I want to loop unroll this many times. But without the pragma, loop unrolling is disabled. Binomial coefficient from the scalar evolution causes issues because the GPU is a 32-bit architecture, and so all math is done in 32 bits. We do have 64-bit software emulated, but once we start getting math operations larger than 64-bit, they get extremely inefficient extremely quickly. So we modified the scalar evolution to limit the bit width of everything to 64 bits maximum. And one of the biggest things is we have to inline everything. This has been talked about in the OpenCL presentation from 2 years ago. On the GPU, you really need to inline everything for it to code gen correctly. And I'll go into some of the constraints of why that is so a little bit later. So the AMD IL Backend is what I've been working on mainly for 2 years with some help from other AMD employees. But it's a production backend that targets AMD IL Language. AMD IL Language is across a pseudo ISA, and I'll go explain more about that soon. The backend itself is mainly self-contained. Now, when I say self-contained, what I mean is I really cannot rely on changes to LLVM core for the backend to work. One of the reasons for this is that I have to support multiple LLVM versions at the same time. We could do this for multiple code bases, but then I have to port my changes from one code base to the other. And the reason we have multiple versions is because I have to have this work across OS X, Linux, and Windows. And Linux and Windows are supported by the Stream SDK, but OS X is part of the operating system. And when, say, Snow Leopard froze, we would move on to a different LLVM version, but Snow Leopard would still be on an older LLVM version. So I had to be able to handle all that. So that's why I say the backend self-contained, I cannot change LLVM core. And from the GPU side, we have to support all GPUs from RV7XX and later. So that's the last 3 years, which isn't too bad, but it's about 4 to 5 new GPUs every year I have to add support for. So going into the target language, which is the AMD IL language. The AMD IL language is a forward-compatible pseudo ISA that's semi-device agnostic. It's also, we don't worry too much about backward compatibility, but mainly just forward compatibility. So what works on the 7XX will work on the Evergreen, or our most recent Northern Island GPUs. The language supports for R300 and later chips. So it was designed about 9 years ago, which it was also designed around graphics, not compute. So when you're doing a compute-based architecture, or OpenCL, which is what our high-level source language is, having all these graphics features are detrimental to the language design. We have a virtual GPR set containing 2 to the 16th registers, but each register is a 4 by 32-bit vector register. We don't have scalar registers. Everything has to be declared before use. So if I want to use a resource, I have to declare it before I can use it. This has conflicts because all resources are globally scoped. So if I have one function that utilizes certain resources and another function utilizes a different set of resources and the sets don't intersect with each other, then we can have resource conflicts. It's a compute-heavy instruction set. So we have over 100 different math-based instructions. We have stuff like cosine, sine, and then also the adds. We have integer-based floating point-based square roots, double-based square roots, reciprocals. So there's a lot of compute-heavy instruction sets, or compute-heavy instructions that are part of this language. We also have macros, flow control, and functions. But one of the interesting is functions are not scoped. So there's no scoping in functions, but macros do have scoping. So if you have two functions that modify register 0, then they'll overwrite each other. But in a macro, you can do that, and they don't overwrite each other. And then we do have flow control. However, we have no unstructured flow control. So LLVM IR only has jumps. So one of the problems of the backend is we have to reconstruct the high-level flow control so that we can output the AMD IL. There's no calling conventions defined because everything is globally scoped, so there's no reason to have a calling convention. We have no extended or truncating memory ops, so everything is just load a certain number of bits and then process that data. So that's caused some issues because there are some memory ops that that always will get generated in LLVM or in the codegen. We have multiple register families. So we have R, which is the GPR register families. We have the L, which is literals. We have CBs, which is read-only constant buffers. X, which is private memory, and then a generic memory register. We have a 32-bit uniform memory region. However, if you want to do byte shortened D-word writes, that's different than doing 32, 64, or 128-bit writes. They're different paths in the hardware, and so they have different resource IDs. And so you have to know these different resource IDs to go down these correct paths. We also have literals. We don't have scalar literals. We have all our literals are vectors, and they're also declared before use. So here's an example of a literal. So I can take a hex value, an integer, or floating point as a literal, and all four of these is one literal value. Then going on to the memory regions, we have 5 different non-uniform memory regions: device memory, constant memory, private memory, GDS, which is an L2 software managed cache equivalent, and then LDS, which is an L1 software managed cache equivalent. OpenCL address spaces, which maps direct to all of them except for GDS. There is no OpenCL address space that maps to that. Inside of device memory itself, we have 137 unique subregions in device memory. 128 of these are read-only image resources. 9 of them are generic 32-bit D-word read-write resources. So with these generic ones, you cannot write 8 or 16-bit values. You can only write, the smallest write is 32 bits. Then we have one generic byte addressable read-write resource, which you can write 8 and 16-bit values, but this also is the slowest path. So to do something efficiently, you want to use the faster paths and not this slow path. Inside the constant memory, we have 16 unique subregions. All the small device memories, like constant, private, GDS, and LDS, they have size limitations that are per device. And on the largest, they're 64 kilobytes in size, but on some devices, they go down to 16 kilobytes in size. So that has to be taken into account if you're going to allocate data correctly. And then, as I mentioned, resource IDs must be known at compile time. So that makes, how do we allocate reads and writes to all these different types of memory if we have to know the resource IDs? So that makes us have to do pointer tracking and a lot of data dependence analysis. So here's some quick examples. So add a register and a literal. That's a vector register between all 4 components, and it's added with a literal, which is the L4. I add a constant in private memory. Again, so we have CB, which is a constant memory, and X, which is a private memory, so like a private array. And we can index into these with the component of a register, but we can't index into them with a register. This is also using the array syntax is the only time you can put a scalar immediate value in the source. If you want to read a 32-bit value, you have this instruction that's not like the other reads for constant and private memory. So this is a read from the device memory. And the reason it's different is because you have to have the ID specified. So the resource ID here is 3, but this is a 32-bit read because the X component is specified instead of the whole vector. But if we want to read a 120-bit value, we then have to get rid of the components and read just the whole vector itself. But if we want to read an 8-bit value or a write, so just change load the stores, we have a completely different type of instruction which has a completely different resource ID. And one of the problems with this is if any write to a pointer is done at an 8 or 16-bit size, every write in every pointer instruction, or every loader stored to that pointer, must use the arena load and not the raw load. And the arena load is less efficient and slower, but it's also, that's why we have to keep track of all the resource IDs between all the pointers. So now getting onto the GPU backend, what's some of the modifications we had to do? I already talked about many of the optimizations we had to disable or modify in the optimization phase. But in the actual backend itself, we have custom passes to handle printf because we don't have a native library support. So we cannot just handle printf normally. Images. There's no way to exactly represent an image in LLVM. So we have an opaque type, and we access that through function calls. And the current way I do this is I embed information in the actual function name itself. This causes function duplication, but I have found no better way to handle this. We do have some GPU-specific people optimizations. So say you have a shift right and a mask. We convert this into a bit extract. Or I need to keep track of, is there pointer differentials? Did someone subtract 2 pointers? Or is there even dynamic pointer assignment? Since I have to know the resource ID, the second you do that, if you have a dynamic pointer assignment, then I don't know the resource ID anymore. This is the one hook I have added to the LLVM core is in selection DAG. There's a part of the code that will turn A and B and C conditional into if A, if B, if C, and that's very inefficient for the GPU. So I've created a bug and added a patch for that. So if you have a very similar hardware, you might want to look into that, see how it helps with your performance. There's been some code gen fixes for vector types. I've pushed some of these back to LLVM core, but some of them I've probably forgot to do. A lot of them have been just removing a search for conditions that are valid, just were not thought of at that time. And then we had to disable the machine common sub-expression elimination in the common code gen passes. So we have to override the whole pass and then override some other information, some private classes, just so we can disable this pass. One reason why I have to disable it is because it conflicts with the CAL compiler and how it does register allocation, because machine common sub-expressionation creates larger live ranges, and that can cause register bloat. So some of the other workarounds to deal with the issue of, say, the resource ID. I actually just found this recently, but ASM printer flags is very useful for one fact that I can store information in the instruction that is specific to the target, to the backend. But the comments say don't put semantic information there, but I need some way to store this information. So I store the resource IDs for all I/O instructions there. I also store load and store specific flags in these instructions, like is this load a cacheable load? There's no way for me to know that to store that information outside of these flags that I've been able to find. Is this an 8 or 16-bit store? Because once this becomes an 8 or 16-bit store, I then have to go find all the I/O instructions that have that same ID and modify what the ASM or what the machine instruction is. Is this a known or unknown resource ID? If it's not a known resource ID, I have to go by default down the slow path. Some workarounds I have in TableGen. So in the GPU, we have a lot of intrinsics. So I've used GCC built-ins to match function calls to native instructions. One of the ways I have to do this is we have square root for the 3 vector types plus doubles. I don't want to generate a TableGen instruction for all of these different intrinsics. So I've hacked around with the intrinsic info class, where I can then map a single function plus the encoding down into a single intrinsic, and then in TableGen I can map that intrinsic to the machine instruction. So that's most of what the backend is, or a lot of things we have changed. So I'm going to go into some ideas that I have on how to make some of these problems easier to deal with. So improvements that I see we could do at LLVM. So in TableGen, having vector immediates would be very useful, because right now TableGen only supports scalar immediates. So I have to have a scalar immediate and then create a vector out of it and then use the vector immediate in a vector instruction. That's not very efficient because there is no vector create instruction in AMD IL, so I have to use integer adds to get that to work correctly. Many-to-many patterns. So there would be lots of cases where instead of having to write IR to IR in the backend, having TableGen be able to do that for you. I think that would be very useful. I know there might have been some talk about this on the mailing list. Function to instruction mapping. So if I could say this is a function call and I want to generate this machine instruction for this function call, I wouldn't have to go through this path of function call to intrinsic and then intrinsic to machine instruction. So they just clean up, make it easier to write all these different intrinsics and not have to have so much code to do one thing. Another thing is register operand to immediate equivalent, or to match the equivalent immediate. So what I mean by this is, say I have an add instruction, and one of the components to the add instruction is immediate value, and the other is a register. Currently, I have to write a pattern to handle register and immediate, and a register and register. I don't want to do that because that bloats the size of my TableGen files. So what I do currently is I match all immediates to load into a register first, and then I use all my patterns are just register to register. There's no immediate pattern matching. But I would like it where TableGen would generate code where we would so if you have an I32 immediate and a register class that handles I32s, it treats them both as an equivalent issue. So on our architecture, this is perfectly fine. So I think this would be very useful. And then methods that act on custom fields and instructions. In TableGen, you can specify some bits. And then you can set those bits while you're in the TableGen files, but I have not found a way to actually access those custom fields from machine instruction class or even the machine operating class. So having a way to do that would be very useful. So now going to LLVM, I mentioned this earlier, but allow expansion of all extended load nodes. Since we don't support any extended load nodes, I don't see why I should have to support any extend when my hardware doesn't support it. So being able to expand not just extended load, but expand as many nodes as possible. Having vector channel encoded, since we are a vector type, being able to encode the vector channels in machine operand would be very useful. Right now, each vector channel requires 3 bits of information. There is a machine operand flag, but it is only an 8-bit field, but I need 12 bits of information. So having ability to encode a vector channel in the machine operand would be useful. And then also having more vector machine-friendly optimizations. A lot of the optimizations that we see are good for a scalar machine, but they're not good for a vector machine. And so, like I said, we've had to disable some. There's still a lot more work we need to do to get our optimization path to be vector machine friendly. And so having people, when they're writing optimization path, how does this work on a vector data type, would be having them focus on, not just focus on it, but not ignore it completely, would be very useful to our development on using LLVM. So that's pretty much it of my talk. Thank you very much.